All right, welcome everybody. Today we're finishing the citric acid cycle and then we're moving on to chapter 28, which is going to be a shift in gears. We're going to jump back into chemistry, or rather chemical new reactions and synthesis. And so there'll be quite a bit to learn there. All right, so last time we talked about the first few steps of the citric acid cycle where we take acetyl-CoA, combine it with oxaloacetate via an aldol reaction and then thioester hydrolysis, and that leads to citrate. We talked about how at that point we sort of lose track of which two carbons are present, or which two carbons in citrate are the, oops, I didn't mean to erase, I wanted a pointer. Which two carbons in citrate are acetyl-CoA because citrate is achiral. And we've got two arms here that are equivalent to each other. We talked about how if the goal of one of the key goals of the citric acid cycle is to lose 2 molecules of CO2, to set us up for that, we might want to have a beta keto acid, but the OH is on the wrong carbon. It is beta to 2 carboxylic acid groups, but it's on a tertiary carbon where it can't be oxidized. So the next 2 steps of the citric acid cycle make sense strategically. We're going to do an E1CB elimination, a dehydration, sort of what we often do after an aldol reaction. Remove a proton alpha to one of the carboxylic acid groups to get an enolate, and then the electrons kick down and OH minus leaves, and that gives us an alpha beta unsaturated carbonyl compound. But we noticed that that alpha beta unsaturated carbonyl compound is alpha beta unsaturated in 2 directions. So blue beta carbon is beta to the blue carbonyl group. Pink beta carbon is beta to the pink carbonyl group. In the step 3, we're going to have water act as a nucleophile to attack one of these 2 beta carbons. If we attacked blue beta carbon, that would be going right back to citrate from this molecule called cis-aconitate. But if we attack at the pink beta carbon, and this is in the same enzyme, then the OH group ends up on the pink beta carbon. It's now at a secondary alcohol, and it can be oxidized. And importantly, if it were oxidized, it would be beta to this carboxylic acid. That would set us up with a beta keto acid, which we've seen do decarboxylations before. Any questions about how we got there? Yeah? Okay. So step 4 and 5 are often shown together, in part because they're step 4 is the one that's catalyzed by the enzyme, and then after we're going to oxidize the secondary alcohol to the ketone, and then we're going to do the decarboxylation. So all of this happens within the context of the same enzyme, though I will show 2 different steps. So isocitrate is the molecule that has the OH group on the pink beta carbon, the secondary carbon. We're going to do an oxidation reaction with NAD+, and we'll get NADH out. A proton will need to be removed. This is basically your standard NAD plus based oxidation. The enzyme that does this reaction is unsurprisingly named isocitrate dehydrogenase. And the effect is going to be to convert that beta hydroxy group into a beta keto group. And the mechanism of this reaction, I won't draw it out in a lot of detail because you have seen this kind of thing before. A base from the enzyme will remove a proton from the beta hydroxy group. Then electrons will kick down to form a new oxygen-carbon pi bond, and hydride will get delivered to NAD+. And those are the arrows I'm not going to draw because you have seen those before, and so you can go back and fill in the details later if you want to. Of course, NADH, this is a payoff molecule. So as we look at the citric acid cycle, this is the first time that we've generated a payoff molecule. NADH can be taken to the electron transport chain within mitochondria to generate ATP. I'll have something at the end when we sort of overview glycolysis in the citric acid cycle. I'll have something to say about how much ATP your body needs to turn over every day just for you to stay alive. Okay, so having established that beta keto acid, we're now ready for decarboxylation. This intermediate is called oxalosuccinate. And once we're there, we're set up for step 5, also in the context of the same enzyme. So I'll just include 4 and 5 here. And this involves the decarboxylation step of a beta keto acid, which doesn't require any special chemical apparatus like we saw in the pyruvate dehydrogenase complex, because when CO2 leaves, the electrons can, from the carbon bond between carbonyl carbon and alpha carbon, can just go on to the alpha carbon where they are stabilized by resonance with the beta keto group. So I'm going to try to redraw the same molecule in roughly the same shape. Here's that pink alpha carbon, and the negative charge is there. Notice that the pink alpha carbon is alpha, let's see, before the reaction it was alpha to the carbonyl carbon, but it's also alpha to the beta carbon. And this enolate now is resonance stabilized, and it will then pick up a proton either from water or from some acidic side chain in the enzyme active site. We don't particularly care which. And then the final product there, notice we've lost 1 CO2. We go from having something that's 6 carbons to something that's only 5 carbons long. 1, 2, 3, 4, 5. And this is called alpha keto glutarate. All right? So as you breathe in and then exhale, some of the CO2 that you're exhaling comes from decarboxylation of oxalosuccinate. That's happening all the time. All right. Yeah?
And just to confirm, it is that same enzyme that catalyzes the decarboxylation reaction?
Yes, and I don't actually know the structure of the enzyme or whether this step needs to be catalyzed at all. It may just be spontaneous. All right, good. Others? All right, so that's 1 molecule of CO2 that we've lost and 1 molecule of NADH that we've generated. Turns out we're not going to wait very long at all for the second equivalent of CO2 to be lost, because if you look at alpha ketoglutarate, it should resemble something you've seen before, which is pyruvate. Both of these are examples of not beta keto acids, but alpha keto acids. And we had a whole pyruvate dehydrogenase complex that we talked about in the previous lecture, whereby you could get that alpha keto acid to decarboxylate. We're going to use completely analogous machinery to do that again with alpha ketoglutarate. Before we do that, I will just pause and tell you that some of these intermediates intersect with other metabolic pathways. And if you want to see all the metabolic pathways in one poster, you can Google it. There are various companies that make these things. You can put them up on a wall, but you'd have to print them and it would sort of be as big as this wall. With computers, you can zoom in, but alpha ketoglutarate is one place where multiple metabolic pathways intersect. You can see actually that alpha ketoglutarate resembles the amino acid glutamic acid. Shoot. This is the amino acid glutamate. And only difference is on the alpha carbon, you've got a ketone versus an amino group. Interestingly, you have seen the chemistry a little bit that interchanges glutamate and alpha ketoglutarate. Again, this is not part of the citric acid cycle. I'm just trying to show you a place where this intermediate intersects with other metabolic pathways. You can go back and forth from here if you used pyridoxamine and what's called transaminase chemistry, or PLP. You learned about PLP and using that to remove an amino group from an amino acid, say to turn tryptophan into serotonin. You can use a similar way to turn glutamate into alpha ketoglutarate, and if you go the other way, you can transfer the amino group. Okay, that's an aside. You will learn about that in biochemistry. I hesitate to even put it in the notes because then you're going to come back and wonder, is that part of the citric acid cycle? Do I need to know that? That's just context. Don't worry about it. Okay, so alpha ketoglutarate is our starting material for step 6. And step 6, I'm not going to show you the mechanism of here because if you go back and review the mechanism for the pyruvate dehydrogenase complex, it's going to be exactly the same. So there is a large enzyme complex called the alpha ketoglutarate dehydrogenase complex. It's going to decarboxylate alpha ketoglutarate and leave you, it's going to break this bond between the carbonyl carbon and the alpha carbon, and it's going to oxidize that ketone carbon to the thioester oxidation state. And the thioester that is going to be with the coenzyme A, thiol, and it's going to leave us with a 4 carbon unit. That'll be our second equivalent of CO2 that's left. And this molecule is called succinyl-CoA. It's going to involve an oxidation step, so we'll convert NAD plus into NADH. Again, that's going to be an energy-rich molecule that we can take to the electron transport chain and exchange it for ATP. And it's going to involve the same cofactors that we saw previously in the pyruvate dehydrogenase complex. It's going to involve FAD, thiamine pyrophosphate, and the lipoate group. I will just abbreviate these. We won't draw the whole structures. That's the 5-membered ring disulfide in lipoate, and then I'll draw just the business end of the thiamine pyrophosphate ylid, or the TPP group. All of these are necessary to make the reaction happen. And I just as review, I will show you this nucleophile TPP attacks the carbonyl carbon of alpha ketoglutarate, and then the resulting negatively charged oxygen picks up a proton. The intermediate looks like this. Oops. I think I've got that right. And it's at that stage that we can do the decarboxylation, and the negatively charged, and the negative charge can go on this carbon where it would be stabilized by resonance. I'm just going to put etc. because you can see the arrows for that in what we talked about for the pyruvate dehydrogenase complex. All right, so if you compare where we are to where we started with something, a 4-carbon unit like this. That's oxaloacetate. We're back to 4 carbons, but we don't have the functional groups all in the right place. So our goal from this point on in steps 7 through 10 is to get back to oxaloacetate, our starting point, and to recover as many equivalents of NADH or FADH2 or ATP or other molecules as we possibly can. So as you can see, this is going to involve some oxidation chemistry. We need to oxidize the alpha carbon here to become not only an alcohol but a ketone. And the other thing is we got to lose the thioester. Thioesters are valuable. Nature could just hydrolyze that and call it good, but nature's actually going to use the thioester to make a molecule of ATP, because thioesters are roughly similar in energy to anhydrides, and that's the kind of bond you've got present in ATP. So our step 7 is going to be converting succinyl-CoA, doing a hydrolysis reaction to convert succinyl-CoA into just the carboxylic acid. But instead of using water to do the hydrolysis reaction, along the way we're going to recover a molecule of, an equivalent molecule of ATP. All right, so you're going to take GDP, which is guanosine diphosphate. That's the guanine version of ATP. And you're going to take inorganic phosphate, which in biochemistry texts is abbreviated as PI. This is just phosphate not bonded to, where none of the oxygens are bonded to carbon. I'm drawing it in this protonation state. One of these OHs could also have a proton based on the pH, and as we've discussed before. These are going to be converted into GTP at the same time that the thioester gets hydrolyzed, and the product is called succinate. It's a 4-carbon diacid, a 4-carbon chain with carboxylic acids on either side. And nature has slightly different uses for GTP versus ATP, but it's roughly equivalent, and you can exchange GTP for ATP, so we can consider that a payoff molecule. Mechanism here, let's see, this reaction is called, the enzyme that catalyzes this reaction is named for the starting material, succinyl-CoA, and then it's called synthetase because it's actually named for the backwards reaction. The synthetase reaction would be a reaction where you take succinate and GTP and coenzyme A and then go backwards and synthesize succinyl-CoA. So again, as I've said before, you kind of have to prepare for this. Enzymes don't care which direction you go for a reaction. The direction that's preferred is governed by thermodynamics. The enzyme only affects kinetics. So the enzyme is going to be named for one of the two directions, forward or reverse, and you sort of have to play it by ear. This happens to be one that's named for the reverse reaction. Okay, mechanistically, this is all simply nucleophilic acyl substitution. So we may abbreviate this or go through it quickly. The negatively charged oxygen on phosphate attacks the carbonyl carbon, and you get a tetrahedral intermediate. Oops, I did that wrong. I'm going to draw out the phosphate group like this just to make it a little bit quicker. 1, 2, 3, 4. And then the coenzyme A thiol leaves. That converts our thioester into a mixed phosphoanhydride. We've seen stuff like this before in glycolysis, in the bisphospho 1,3 bisphosphoglycerate. We had a similar mixed phosphoanhydride, and we did a similar substrate level phosphorylation. Essentially, you're going to have the oxygen from the beta phosphate group of GDP attack the phosphorus to generate a pentavalent intermediate. In which phosphorus has 4 things attached to it. And then maybe if it's okay, I'm going to abbreviate the rest of the molecule as just GMP. Then electrons on one of the oxygens will kick off the carboxylate leaving group, and that gives us the products. Succinate, GTP, and the coenzyme A thiol. All right, so that's sort of analogous to the substrate level phosphorylation involving 1,3-bisphosphoglycerate in glycolysis, and its recovery of a molecule that's basically equivalent to ATP. All right. I like that step because it shows you that nature does not waste thioesters. We're not hydrolyzing a thioester for no reason. We're recovering an energy-rich molecule. Okay, so again, comparing where we need to be, we want to get to oxalosuccinate. We've hydrolyzed the thioester, check. The remaining steps are all going to be about oxidizing this alpha carbon to a ketone. And there are 3 steps left. So the strategy is you're going to take succinate, and we're basically going to do, again, an E1CB style elimination, only the thing we're going to deprotonate the alpha carbon, but the thing we're going to be eliminating is a hydride from the beta carbon. And the molecule that's going to receive that hydride is not NAD+, but is rather FAD. And the energy-rich molecule we get out here is called FADH2. FADH2 has a different reduction potential than NADH, so it intercepts the electron transport chain at a slightly downstream area, so we don't get quite as many molecules of ATP per molecule of FADH2. The enzyme, however, that catalyzes this reaction is named sensibly succinate dehydrogenase, and the product is an alpha-beta unsaturated carbonyl compound, a double bond in between the alpha and the beta carbons, and this is called fumarate. And I don't know, I always remember fumarate because it has embedded in it is the infinitive form of the Spanish verb to smoke, or fumar. I don't know why, but I guess I just noticed that. It's kind of one of those dumb things that you wish you hadn't noticed because it doesn't mean anything, but I can't not notice it, so there it is. All right, mechanism here is going to be base removes the alpha proton to make an enolate. Nothing unusual there. Once you've made the enolate, then the negatively charged carbon, alpha carbon, is going to kick off a hydride as a leaving group, but that hydride is going to be handed off directly to FADH2. And if you look at the structures of the enzymes that catalyze these sort of dehydrogenase type reactions, hydride really is handed off directly. The hydrogen is within touching distance of the FAD molecule or NAD+ molecule even before it gets transferred. So you don't need to worry about hydride being a terrible leaving group, which of course it is, because it doesn't actually leave, it's just directly handed off. So electrons kick down, hydride is delivered to this nitrogen, the remaining arrows go like this and end up picking up a proton and putting it on this other nitrogen, and that gives us our products, fumarate and FADH2. I won't draw the structure of FADH2, mostly because we're in a hurry, also because the arrows here give you the instructions and you can look up what that structure is previously in your notes. All right. So again, comparing where we are to where we need to be, if you were going to try to plan out a synthesis, we need to get an oxygen on one of those two carbons. At this point, fumarate is totally symmetrical. We can call this one alpha and this one beta relative to this carbonyl, but this alpha carbon is beta to that carbonyl. So essentially at this point, we need to get an oxygen on one of these two carbons, and then we need it to be a ketone. We're set up to do that because this is an alpha-beta unsaturated carbonyl compound, and so we can do conjugate addition. I'm going to erase oxaloacetate because I don't want you coming back to your notes and thinking, is that a product of this reaction? No, we're just trying to still envision where we need to be. So this is step 9 of the citric acid cycle. We're basically going to do conjugate addition. We'll call this the carbonyl carbon, this the alpha carbon, this the beta carbon. Conjugate addition of water, some base, a basic side chain in the enzyme active site will deprotonate water. Hydroxide will attack the beta carbon, and we'll get an intermediate where electrons are on the alpha carbon will make this enolate, which is the product of a conjugate addition. The enzyme controls the stereochemistry of addition to the beta carbon, and you end up getting a stereocenter with that configuration. That enolate intermediate is then protonated on the alpha carbon by an enzyme side chain, perhaps the conjugate acid of the basic side chain that removed the proton from water in the first place. And the final product here is called L-malate. L is the configuration of that stereocenter in old-timey language. As I said, the mechanism is simply conjugate addition. And the enzyme that does this is called fumarase. It's the enzyme that acts on fumarate and converts it into L-malate. And again, they're naming it for one of the directions of the reaction. Okay, now you can see where we're going. The next step makes total sense and you could predict it. To get to oxaloacetate, we simply need to oxidize malate, oxidize the secondary alcohol of malate to the ketone. And so malate is our starting point. The enzyme, again, here is named, unsurprisingly, malate dehydrogenase. And this is another simple NAD+ based oxidation to generate NADH. A base from the enzyme will remove a proton from the alcohol of malate. Then electrons will kick down to form a new oxygen-carbon pi bond, and the hydride on that secondary alcohol, that hydride will leave and be handed off directly to NAD+ to give you NADH. And that completes the cycle. Oops. Now we're back to oxaloacetate. And we're ready to go back to step one and accept another equivalent of acetyl-CoA. And so the process keeps on turning. The course of the citric acid cycle is one eternal round, without beginning of days or end of years. Well, actually, it begins when you, suppose it begins when cells, when does it begin? I don't know, I got nothing. Okay, so, that's all of the chemistry. Is there any particular step you want to look at or review? Yes?
Question, when, at the very beginning of the cycle, where we do end up hydrolyzing a thioester, is there a reason why hydrolysis occurs there? And
Right. Yeah, that's a good question. At the beginning, we do an aldol reaction and then hydrolysis. And the question could be, why aren't we taking advantage of that thioester? That's a good question. The answer is probably related to the relative stability of starting materials versus products. I haven't written the delta G's for each of these steps. It may also, one other reason for, so basically the first answer is I don't know. The second, but it may have something to do with maybe this reaction's a little bit unfavorable, so you need to, and aldol reactions are reversible, so you need to make it less reversible by hydrolyzing the thioester. That would be one explanation. A related explanation is that once you do, if you hydrolyze the thioester, those two carbons are now committed. You can't go back. So I guess that's the same thing. Yeah, the short answer is I don't know. Second answer has it probably has to do with committing a full equivalent of acetyl-CoA without going backwards, but you're right. You could have envisioned a similar step to convert that thioester into a molecule of ATP, and it seems like the thermodynamics just must not work out very well for that. Yeah?
Why do we spend so much energy making the thioester to just immediately turn it back into an ester in that first step?
Yeah, that's why do we, remember that acetyl-CoA, we get that from either the pyruvate dehydrogenase complex or from fatty acid metabolism. And a good question is, why does nature use that thioester to begin with? Are there other alternatives? And why do we have that relatively energy-rich thioester and then turn around after the aldol step and just hydrolyze it? And would there have been another option? Could nature have done something like we did in step, whatever it was, the succinyl-CoA step 7 of the citric acid cycle, where we finagled another molecule of ATP out of here? I don't know. To do that, you would need to compare what the delta G of this reaction is to what the delta G of ATP synthesis is. My guess is that the delta G of this reaction isn't favorable enough to where you could tack on ATP synthesis and still have it be favorable. But that's a good question that I don't really know the answer to. I'm just speculating at this point. Yeah?
Sorry, another quick question. Whenever we have a step involving TEP and lactic acid, is the NAD just coming from the regeneration of the lipoid?
Right. So remember, there are 3 different reactions that happen here in this alpha ketoglutarate dehydrogenase complex. You first have step 1 is oxidative decarboxylation. And we can review that if we want to go back and look at that pyruvate dehydrogenase complex. The second is called trans-thioesterification. That's where we're going to generate acetyl-CoA. And then the third step is to regenerate lipoate, and that's where we also get NADH out. You have seen the mechanism for the first step. The second mechanism is not hard. That's nucleophilic acyl substitution. I didn't show you the mechanism for the third step. Yep. Okay, others? All right, so with a little bit of math and a little bit of review, we can actually go back and try to figure out what's gone on. Here is what happened in glycolysis. I lost where we were. There we are. So sort of summarizing what we're getting out of glucose, and then summarizing what we're getting out of the citric acid cycle, which I think I overviewed at the beginning last time. Nope. There we go. All right, so overall, I'm not going to write a balanced equation. We could, but this is not general chemistry. I just sort of want to know what we're getting out. From 1 molecule of glucose, we're getting out, let's see, 2 ATP from glycolysis. We're getting 2 NADHs from glycolysis and 6 NADHs from the citric acid cycle. So that's 8 NADHs overall. We can go count the NADHs that we get. Let's just look for the explosions with NADHs inside. That's 1, 2, and then 3. For 1 acetyl-CoA, remember 2 glucoses lead to 2 pyruvates, which lead to 2 acetyl-CoAs. So that's 6 NADHs. from the citric acid cycle, 8 overall. Then we're also going to get 2 FADH2s and then 2 GTPs. And we're going to consider those GTPs basically equivalent to 2 ATPs. Then, in terms of the conversion factor for in the electron transport chain, which you'll learn about in biochemistry, the conversion factor of NADH versus FADH2 to ATP depends on a lot of things. It depends on how the electron transport chain works by having NADH and FADH2 drive what's called a proton gradient across the mitochondria. You'll learn about that. But membranes are leaky, and so if the proton gradient isn't 100% efficient, you don't get the maximum amount of ATP out. A decent estimate, I said 3 and 2 earlier, it turns out that's probably wildly optimistic in terms of reality. A more realistic number that you can get is maybe 2.5 ATP per NADH from the electron transport chain, and then maybe 1.5 ATP per FADH2. So if we do a little bit of math for that, I'm not, 2.5 times 8, okay. Somebody do that fast because I'm gonna embarrass myself. 1620? Okay. And then 2, that's 3 over here. So if we add it all up, 20 plus 3 plus 2 plus 2, I hate arithmetic. 30? Around 30 ATP overall. Well, if it's wrong, tell me. It's 27? Thank you. Could you believe this is so, I'm embarrassed because I have a PhD, but not in math. But it's not in math, so what are you gonna do? The other day, I have a birthday in June, and in primary, we announce birthdays once a month, and so the kids were somewhat excited to learn that I have a birthday. I don't know why. Everybody has a birthday, but this month is mine. And they're like, how old are you? And they started guessing. 67, no. 20, no. And I told them the wrong number. I'm like, this year I'm turning 46. I was born in 1979. This year I turned 45. It was really quite I didn't actually realize that I'd made a mistake until the end. My friend, who's also my dentist, and I guess knows my birthday, that's kind of creepy, but maybe he has a memory for that, is like, Josh, you're turning 45 this year. I'm like, right. Okay, 27 ATPs per glucose. Now, why are we worrying about this? I just want to take a step back and think about what you need to survive. So you use ATP for everything. Go ahead. I was working up to something, Isabella. You're interrupting.
So sorry.
Okay, go ahead.
Do we consider the 2 NADHs that might come from conversion pyruvate to acetyl-CoA?
Oh, we didn't do that, did we? Okay, so actually, plus 2, thank you for that. It's 2 NADHs from the PDC. So that's going to be another 5 ATP, right? Yes? So actually, erase 32? Yes. Okay, 32 molecules of ATP per glucose. Now, how much does your body actually need to survive? It's thought, the numbers here are astronomical, but it's thought that you need to use about 100 to 150 And these are in concentration units, so you need to know your volume to figure out about 100 to 150 moles per liter daily. I'm not sure what the volume of the human body is. Does anybody want to look that up? Hey Siri, what is the approximate volume in liters of the human body?
For example, the human body has a volume of roughly 26 gallons, 0.1 cubic meter or 100 liters.
Thank you.
This
Wow.
is from Encyclopedia.
No, I don't need to know that. Okay, so about 100? Okay, how many molecules is in a mole? 6 times 10 to the 23. So we just accounted for 32 of those. So you've got a sense for how many times this has got to happen just to keep you alive every day. You could calculate, therefore, how many grams of glucose you need every day to survive. Now, does your body actually have that much ATP on hand? It turns out no. Your body only has anywhere between 80 to 100 grams of ATP. So that means each individual molecule of ATP is probably recycled anywhere between 1,000 to 1,500 times a day. So all of these cycles are turning like crazy just to keep you going. And why are you breathing oxygen? Well, that's another story. That's also connected to the electron transport chain and driving the proton gradient. Okay, so we've had a crash course through biology and through biochemistry. We've just scratched the surface, but hopefully you have an idea of the kinds of reactions that biochemistry is using to keep you alive. All right, that's a decent stopping point. Let's pause there. When we come back, you gotta get your synthesis hats back on because we're gonna be talking about carbon-carbon bond forming reactions, and importantly, we're gonna be talking about transition metals, which is something you probably haven't thought of at all since general chemistry, and even then not that much. So we're gonna dive into that after the break.